Next up, we have Ilia Muravev from the Saint-Petersburg State University, who will tell us about some work that he did together with Semyon Grigorev, also from Saint-Petersburg State University. And the topic is universal high-performance CFL reachability via matrix multiplication.
Thank you. Hello everyone. My name is Ilia. I'm from a company called Exploit, and today I'll be presenting universal high-performance CFL reachability via matrix multiplication, which is the work I did with Semyon Grigorev. So first of all, let's talk about what context-free language reachability is and why we care about it in static analysis. Let's start with a very common problem, which is determining if the value of some variable A can flow into another variable B. You can imagine how this problem arises in all the different types of static analysis, but how do we actually solve it? Let's say we have a very simple program. It consists of an identity function called ID and a main function that calls the identity function twice. Here, A flows into B because ID of A is assigned to B, while C doesn't flow into B because ID of C is unused. But if we naively construct a sparse value flow graph, we'll see that A reaches B, which is expected, but also C reaches B. So we need some way to discard the path from C to B while preserving the path from A to B. One such way was proposed by Thomas Rebs, and the idea here is to use edge labels. We use opening parentheses for the edges that correspond to function calls, and we use closing parentheses for the edges that correspond to function returns. And we also use subscripts to differentiate between different call sites. And now we only consider those passes whose labels form a well-nested parentheses string. That is to say, they form a word from the Dyke language. For example, the path from A to B is well-nested, so A can flow into B, while the path from C to B is not well-nested, so C cannot flow into B. In this particular example, we focused on the Dyke language, but in general, in CFL reachability, any context-free language can be used to impose the path constraints. For example, if we want an analysis that is both context-sensitive and field-sensitive, we can use various context-free approximations of the interleaved Dyke language. So how do we actually compute CFL reachability? First of all, we receive the path constraints in the form of a context-free grammar. In the case of the Dyke language, the grammar may look like this. Next, we identify the rules that have more than two symbols on the right-hand side. Here it is the third rule, and we simplify such rules. Here we do it by introducing a new symbol called n. And now that we have a simplified grammar, we can start adding new edges to the graph. First, we look at epsilon rules. Here we have an epsilon rule for the symbol s, so we add a self-loop labeled s for each vertex of the graph. Next, we can look at vertices x and b, and notice that there is an edge labeled s followed by a closing parenthesis edge, so we can use the force production rule to concatenate those and create a summary edge labeled n1. Here we use the subscript of 1 because the closing parenthesis has a subscript of 1. And now we have an opening parenthesis h from a to x followed by an edge labeled n1 from x to b. And here we can use the third production rule to create yet another summary edge. And this time, this edge is labeled S, so we know that A reaches B via a well-nested path. Notice how we can't apply the same logic to create a summary edge from C to B, because in this case, the subscript of the opening parenthesis doesn't match the subscript of N. All of this can be quite compactly translated into the language of linear algebra. This is important because linear algebra operations are highly efficient on modern hardware. Okay, so the graph is naturally translated into the adjacency matrix, whose elements are sets of symbols. And as for the grammar, we map its rules to the set multiplication rules. And now that we have the set multiplication operation defined, we define the set addition operation simply as the set union operation, and we can start propagating CFL-reachability via matrix multiplication. For example, if we multiply the adjacency matrix by itself, we'll find out that there should be a summary H labeled N1 from X to B. And this brings us to a baseline matrix-based algorithm for CFL-reachability called MatrixCFPQ. This algorithm is very simple. It starts with an adjacency matrix T and then keeps adding T squared to T until a fixed point is reached. This is pretty much the same as the classic Floyd-Warshall algorithm, with the only difference being that the matrix elements are sets. Matrix addition is actually an element-wise set union, and multiplication is defined with respect to the grammar. Originally, MatrixCFPQ was proposed in the context of graph databases and evaluated on navigational queries. Here, the bar graph shows query execution times. MatrixCFPQ is shown in red. And as we can see in this domain, it outperforms other universal CFL-reachability solvers. But navigational queries on RDF graphs are unrelated to program analysis. So naturally, we tried running MatrixCFPQ on program analysis tasks. We took a few datasets that contain C, C++, and Java program graphs, and grammars used for value flow, alias, and points to analyses of different levels of sensitivity. And here are the execution times we've got. Here, MatrixCFPQ is still shown in red, and as we can see, on program analysis tasks, it is no longer in a clear lead. In fact, in the majority of the cases, MatrixCFPQ actually exceeds the timeout of 3 hours. Here I use small crosses to show cases where we have timeouts and also to show cases where some non-universal solvers are simply incompatible with a particular analysis. So why is MatrixCFPQ so much slower on program analysis tasks? There are actually 2 reasons for that. First of all, these tasks typically require many more iterations for convergence. And secondly, we often use quite large grammars for program analysis. That's because when we want field sensitivity, we add a separate production rule for each field. And when we want context sensitivity, we add a separate production rule for each call site. So how do we deal with the first problem of having too many expensive iterations? Here, we need to realize that on the later iterations, the matrix T barely changes, so we can speed up things a lot, especially speed up sparse matrix multiplication by only considering those elements of the matrix T that actually change. In other words, we can replace T times T with T times delta T, where delta T is simply the last change of the matrix T. And we also need to remember that matrix multiplication is not commutative, so we need to multiply T by delta T both on the left and on the right. Okay, let's look at how this first straightforward optimization impacts the execution time. Here, the baseline is shown in red. Incremental MatrixCFPQ is shown in orange, and in cyan, we have the previous state of the art. As we can see, the incremental version is certainly faster than the baseline, but doesn't quite reach the performance of the previous state of the art. Before we can tackle the next issue, that is poor scalability with respect to the grammar size, we need to talk about how the baseline MatrixCFPQ represents the adjacency matrix in memory. The thing is, linear algebra libraries work best when matrix elements have a fixed size. But in our case, matrix elements are sets of different sizes. The original authors of MatrixCFPQ recognized this problem and decomposed matrix T into multiple Boolean matrices. For each symbol x, they created a separate Boolean matrix T superscript x that simply shows which cells of the original matrix contains the element x. Using this Boolean-based representation, we can compute, let's say, T times T by simply multiplying appropriate Boolean matrices chosen based on the production rules. For example, let's consider the production rule for the symbol n from the Dyke language grammar we looked at earlier. From this rule, it follows that for each value of I, we can compute t times t superscript ni by simply multiplying ts by t opening parenthesis I. As you can see, the number of Boolean matrix multiplications the baseline MatrixCFPQ needs is equal to the number of call sites. In our implementation, we utilize linear algebra libraries better and do all of these multiplications in batch by simply using block matrix multiplications. So let's look at execution times once again. Here the version of MatrixCFPQ with all discussed optimizations is shown in yellow. We can see that it is significantly faster than the previous version and that it also starts to get competitive with the previous state of the art. But we still have 3 more optimizations to go. The first of these 3 is optimizing matrix formats. The thing is, some matrix multiplications are faster in row major formats, while others are faster in column major formats. So we actually maintain 2 copies of the matrix T, so we can choose an appropriately formatted copy based on the multiplication we perform. And at this point, we spend so much effort optimizing multiplications that actually additions often becomes a bottleneck. The issue here is that on each iteration, we add an extremely sparse matrix delta T to a much more dense matrix T. And that causes a complete reconstruction of the whole matrix T. And to deal with that, we actually don't perform the addition and simply memorize all the matrices that need to be added together in a set of matrices called T tilde. So now when we need to multiply, let's say, delta T by T, we actually need to multiply delta T by each matrix in the set T tilde. So if we let this set grow uncontrollably, we will soon end up with too many multiplications. So to deal with that, at the end of each iteration, we actually have a partial merge phase, during which we try to identify matrices of similar sparsity and actually sum up those matrices. Okay, so let's look at execution times. Here, yet another version of MatrixCFPQ is shown in green. We can see that in some cases, the 2 optimizations I just described actually result in a slight slowdown, but overall we get a significant speed up. And most importantly, we actually reach the state-of-the-art performance in the majority of the cases, and we still have 1 more optimization to go. This last optimization is related to the fact that the same context tree language can be generated by different context tree grammars. And actually, for 2 grammars from the CFPQ dataset, we found equivalent grammars that result in a better performance of the respective analyses. This last optimization is purely empirical, so all I can do is show you execution times one last time. Here, our final version of MatrixCFPQ is shown in dark green. We can see that it is much faster than the baseline, and that it is also faster than the previous state-of-the-art across different static analyses. Of course, there are some exceptions. For example, in the leftmost case, the fastest solver is actually Gigascale, and that's because for this particular analysis, there exists a specialized data structure that Gigascale uses. Okay, so far I've only talked about execution time, but we also need to consider correctness and memory efficiency. So first up, correctness. In all considered cases, optimized MatrixCFPQ obtained results aligned with other solvers. In terms of memory efficiency, our solver is generally in the lead. On a geometric mean basis, it uses about 30% less memory than the second best, thanks to efficient memory management in the linear algebra library. Although I need to say that in rare cases, other much slower solvers do use less memory. In the future, we plan to generalize our optimizations to other variants of MatrixCFPQ. Specifically, we want to target multiple source MatrixCFPQ, since it can be used in on-demand analysis. And we also want to look at all passes MatrixCFPQ, since it can be used in a mutual refinement algorithm for interleaved Dyke reachability, which itself enables analyses that are both context-sensitive and field-sensitive. And besides that, we also plan to further boost the performance by avoiding some redundant derivations and offloading the most intensive computations to GPUs. And that's pretty much it. Thank you.
So are there questions for Ilia? So maybe I can get the ball going. So you said that for different grammars, your approach, the efficiency differs. Could you characterize what makes a grammar better or worse suited for your approach?
Basically, what we did, of course, thank you for your question. And what we did is run our approach and profiled which grammar rules take the longest time to process. And we don't have much intuition of it. Right now, we use kind of greedy approach to eliminate these rules and replace them with different rules, or run it again, identify worst performing rules, and replace that. So I think it needs more studying to understand which rules are worse and which rules are better in terms of performance.
Thanks. Then Xavier has the next question.
It's working. Thanks a lot. Yeah, thanks a lot for the presentation. So if I understand well, your end goal is to offload the computation to the GPU, as you just said. So in previous works where people try to do this with some part of the abstract domain representation, one effect that was observed is that in the transfer of data from normal memory to GPU, there is some offset, some cost that comes up. And that can actually be more than what you gain by doing some of the computation on the GPU. So do you think this will be a problem in your case, or did you not consider this at this point quite yet?
Thank you for your question. It is indeed true that transferring data to the GPU is can be more costly than actually performing the operations. And here we have some results with the baseline MatrixCFPQ. It's not actually really our results, it's other people worked on running baseline MatrixCFPQ for RDF graphs on the GPU, and they got the performance boost. But in our case, the performance boost may be less because our optimizations actually make matrices more sparse, which diminishes performance boost. And also, we don't really need to perform all the operations on GPU. There are some recent works that use approaches that combine CPUs and GPUs and actually even perform the single matrix multiplication operation partially on GPU and partially on CPU. And perhaps we can benefit from that.
Okay, thank you.
And that's for sparse matrix multiplication, I need to clarify probably.
Just to give one reference I was thinking about some work by, I think, Jacobazzi and a group of people with him, where they actually turned some numerical abstract domains into GPU, and I believe that was octagons, and they had the effect I mentioned. So
the work I mentioned is not about static analysis at all. It's a work titled Heterogeneous Approach to SPGEM. I think something like that. And SPGEM stands for Sparse General Matrix Multiplication.
So we have time for one last question, which comes from over here.
Thanks for the talk. So regarding the representation of matrix, as you presented, so when the age has symbolic values, like the example you showed in the very beginning, the context sensitivity, right? So how do you efficiently process those symbolic values? And some values may just like the transitive, right? Transitivity. And some values has to, you have to be aware of those context sensitive matching. Would this affect the effectiveness when you do this multiplication?
Okay, let me go back to the slide you mentioned. You probably are talking about this slide. And we actually don't run any symbolic execution or any abstract interpretation. So we actually care about data flow analysis without caring which values are
But
flowing.
imagine if you traverse from A to B, right? So you need to match the calling context, the return size as well. Then you basically, in classical way, you have to like basically match them and pop those from the stack. So once you reach from A to B, then B you don't have any symbolic value when you keep traversing. So how would you handle this in the matrix multiplication?
Oh, it's via the grammar. We have, let me find the slide. We have the grammar defined via how we define matrix multiplication. When we multiply an opening parenthesis 1 by n1, we get a set containing s. But when we multiply an opening parenthesis 2, let's say, by n1, we get an empty set.
Okay, probably in the interest of time, we can talk offline.
All right, so let's thank Ilia one last time.